Welcome to Chapter 7, Part 2 on Solutions to the Solow Growth Model. Last time, we solved the model out, and we found the steady states for all the endogenous variables in the model. So that was like capital, investment, output, consumption, all that fun stuff. And then we saw some graphs, we saw a little bit of math, got kind of a visual idea of what the hell this looked like and really what we were doing. And I went off on a little bit of a tangent for a minute to explain some comparative statics, which was like changing the savings rate, depreciation, things like that. But I didn't really go into it explicitly. So we're going to do a lot of that today. We're going to really get to some of the meanings of the model, why we care about it in the first place, and sort of what a real world example of growth would be like. Now, that gives me a nice little segue into some optimality regarding consumption in the steady state. So I get steady state consumption, and I take one particle of unobtainium, have a nuclear reaction, flux capacitor, carry the two, change atomic isotone into a radioactive spider, run through some calculus via the implicit function theorem, and I get savings times output equals delta times steady state capital. Okay. Savings times steady state steady state output investment, right, equals the depreciation rate times steady state capital. Okay, well, let's think about that for a second. It tells me investment in the steady state is equal to depreciation times steady state capital. So really what we're looking at here is the law of motion of capital in the steady state. And I've just kind of substituted some stuff out so that I've got, instead of investment equals delta KSS, I have S times output equals delta KSS. F you, science. Moving on. One more thing here. So if we were to differentiate the consumption function, and we wanted to maximize it, right? So take derivative, set it equal to 0. What I end up with is the marginal product of capital in the steady state being equal to depreciation. It's what you see in equation 1. Okay, what is that? Well, think about this for a second. The marginal product of capital, that's the return on capital, right? It's how much additional output I'm going to get given one additional unit of capital being applied to production. And if that equals the rate of depreciation, then the only value that will actually satisfy the model in the steady state, in hopes of having a goal where everything is stationary, would be the rate of depreciation being equal to savings, right? So the savings rate is equal to depreciation. So if capital's falling apart at, say, 5%, then we're going to be saving at 5%. That's going to keep everything stationary, which makes sense, basically. You know, we're not adding any additional capital. We're not losing any capital. We're really just kind of keeping everything the same. Now, this does, of course, assume zero population growth. If we had population growth, we would have to account for that as well. And if it grew at, say, a rate of n, right, n could be like 1%, 2%, 10%, whatever, then the savings rate would be equal to the rate of depreciation plus population growth. Okay. In the absence, though, of population growth, because I didn't really want to give you guys a ton of stuff with population growth. It's like you guys already saw a lot of math anyways, so I made a simplifying assumption that population growth was 0. Thus, you will almost universally have to deal with delta equals S, nothing else. Now, this is what is known as the golden rule, and we call it that because it's the rule that maximizes steady state consumption, and it means the amount of savings that maximizes steady state consumption maximizes tomorrow's consumption and the next day's, and so on and so forth, which really means we're treating future generations the way that we want to be treated ourselves, thus being called the quote-unquote golden rule. Now, if the economy is below steady state capital, well, we have a higher savings rate, which will then decrease consumption, right? You save more, you consume less. If the economy is above steady state capital, the economy will consume more and then save less. So essentially what's happening is if we're below steady state capital, we converge to steady state capital, right, from below. So, you know, our steady states will sort of increase up to that steady state capital G, golden rule. If the economy is above that, right, we're saving too little, or we're saving too much, consuming too little. So we save less, consume more. So really, in the second case there, saving less means that the capital-labor ratio is too high. Households were saving too much and not consuming enough. This is what's known as dynamic inefficiency. So if we have a steady-state capital-labor ratio, because remember, everything was in effective labor units. It was one of the first things I did with the model. I divided everything out by L. But the steady state here isn't really the only thing that we care about. I mean, steady states are cool, but we really care more about like an equilibrium path. Now, this part I stole directly from Daron Acemoglu. I claim none of this for myself. But the term equilibrium is used a little differently in economics than it is in like engineering and physics. Right? In engineering and physics, the term equilibrium is used to describe a dynamical system at rest. But not so much the case in economics, right? Because when we have like an equilibrium in economics, supply equals demand, it's not necessarily to say everything is at rest, right? You can have a lot of things having to move around to maintain that equilibrium. So if it were the case, right, that everything was completely at rest, then if the economy was away from the steady state, it would be in disequilibrium. But that's not really true. Non-steady state behavior is still going to be governed by market clearing and optimizing behavior of both households and firms. So the market can be in equilibrium even though we're not in a steady state. Because markets can still clear, it's just it won't be the most optimal market clearing that we're looking at. Now, most economies really spend their time away from the steady state because everything's constantly moving around and things are changing. And so it's not like we all just converge to a steady state and go, hey, we're in a steady state now. Let's just sit here and do nothing. It doesn't really work that way, right? It's kind of like a paradigm, right? It's this nice little perfect view of the world that we would like to be in a steady state. So we're generally moving towards a steady state, but we're not always in a steady state. However, markets are generally clearing along the way. So we're really interested in like the entire dynamic equilibrium path of the economy, not just the steady state, right? So we're not concerned about being in the steady state. We're also concerned about how we get to the steady state. It's a little bit more interesting, right? Because everything being perfect and solved out and all that stuff, that's nice. You don't get anything useful out of that. You don't get anything interesting, nothing that makes you go like, oh, wow, I want to learn more about this stuff. So to understand what the equilibrium path looks like, we got to look at some transitional dynamics, right, of the equilibrium difference equation starting from, say, some arbitrary capital-labor ratio. And we're going to be really interested in how the economy behaves as it gets closer to the steady state. So if we have some arbitrary, like, endowment of resources, right, we start at some level of capital that's, say, below the steady state, right, the economy will follow the law of motion as it gets closer and closer and closer to the steady state. Now, there's a lot of stability conditions required to make sure that this happens. And ultimately, if we have coefficients that are going to be less than 1, then we get everything we need for a globally stable equilibrium steady state. Now, in this case, you don't have to worry about that. It will always be a globally stable steady state for this system. So what we're going to do is we're going to plot out the dynamic evolution of the capital stock. So instead of a graph with y on the vertical axis, k on the horizontal axis, right, we could have kt plus 1 on the vertical, k on the horizontal. And if we were to plot out the function, right, kt plus 1 equals f of kt, it's the investment flow equation, because investment is equal to savings, which is equal to a constant fraction of income, times income, what we would have is kt plus 1 equals investment plus 1 minus delta times kt. But of course, what we could also do is we could just set the equation equal to a 45-degree line. And that would be the same as setting every kt and kt plus 1 equal to k star. And I want you to think about why. If you need to pause this and think about why, feel free to do so. Now, the point kt equals kt plus 1 equals k star is a fixed point, or it's achieved steady state capital. So So we could solve for it by setting every KT and KT plus 1 equal to K star or KSS. K star and KSS are the same thing here. We can go from there. And if we do that, that would give us the now all too familiar solution to the Solow model, right? So equation 4 is steady state capital. Because of the stability of this dynamical system, the fixed point is what's known as an attractor, which means if we move away from the steady state and we try to iterate forward, okay, it's going to have, period 1, period 2, period 3, period 4. If we solve it out, we end up converging back towards it, not away from it. In economics terms, it means that when the economy starts with too little of the capital relative to labor supply, the capital-labor ratio increases. And the reason this happens is because agents in the economy will save more until they get up to the steady state. So it's really governed by behavior of the marginal product of capital, hence the return to capital, right? If you have a high marginal product of capital, right, you've got less capital than, say, what we should be at the steady state. As we save more, that marginal product of capital will fall because of diminishing returns to capital, and then we would also see an increase in the wage rate, which isn't explicitly modeled here. If the economy starts out with too much capital, well, then you dissave, right, which means that you're not saving, and in the process, the wage rate declines, and the rate of return to capital will increase, and thus we would converge back to the steady state. So if I've got KT plus 1 against KT, and I have this 45-degree line, then what happens is, and I plot out investment here, if I've got K naught being lower than, say, K star or KSS, then essentially I will save more and consume less. And I will continue to do that up until the point that steady state capital is achieved, where K star equals KT equals KT plus 1, right? So at any point along that red 45-degree line, steady state capital is achieved. So wherever the investment curve crosses that 45-degree line, we get steady state capital. Now, this is not the case. Take a look at the graph here, right? This is not going to be the case like, y as a function of k. This is KT plus 1 plotted against KT. So make sure when you're looking at the setup of the graph, you are aware of really which one you're looking at here. So wherever investment crosses that 45-degree line, you achieve steady state capital. So let's talk about steady state capital, all right, which is given by equation 5. Now, this is the steady state capital where we have the possibility of growth, right? Total factor productivity, A. And from this, we can see a couple of things, right? Mathematically, well, S and A are in the numerator, delta's in the denominator. Let's think about these fractions for a minute here. If we got positive stuff in the numerator, right, it's going to increase the number's value. If we have positive stuff in the denominator, it's going to decrease the number's value. In this case, it's going to decrease steady state capital. Let's get into the significance of that, because this isn't just pure mathematics. This is kind of where mathematics and economics come together. And if we chug through some numbers here, we'll see why. So let's say savings is 5%, depreciation is 3%, A is 1, right? So there's no technological growth, and alpha is 1/2. What is steady state capital going to be? Well, I plug everything in, right? Just using this formula right here, equation 5. I plug everything in, and I get steady state capital being 2.7. But now let's say I want to increase my savings to 0.1. So instead of 5%, I increase it to 10%. What happens then? What do you think would happen if I increase my savings rate? Looking at equation 5, right? We're not even going to go through any math just yet. Just look at equation 5 and tell me what you think would happen to steady state capital if I increase savings. Now, based on what I say on this slide, it should increase the number's value, right? It should increase steady state capital. But let's see how and why. All right. Now I've got savings equals 0.1. So I plug that in. All right. I evaluate everything. Well, now steady state capital is a lot larger. It's 11.1. So if I increase savings, then steady state output will increase. So if savings goes up, KSS goes up. Okay, I guess that makes sense, right? If you're saving more, right, you're investing more. If you have an increase in investment, that means steady state capital is increasing because you're investing more. We're getting our hands on more capital. So steady state capital is going up. And then, of course, if steady state capital is going up, steady state output is going up. So what about delta, right? If I increase depreciation, what happens? Well, let's increase depreciation from 0.03 to 0.05 with savings at 0.05 and alpha at 1/2. Well, I plug everything in, I evaluate it, and I get KSS equals 1. All right. So originally it was 2.7 with depreciation at 3%. Depreciation at 5%, it drops down to 1. So if delta increases, steady state capital falls, which also makes intuitive sense, right? If capital's falling apart at a faster rate and we're not doing anything to save more, well, we're going to have less capital in the steady state because we're not replacing capital quickly enough to keep capital where it is. So in the steady state, if depreciation goes up, capital is going to fall. Hence, depreciation being in the denominator implies steady state capital will decrease. So we get something that makes both mathematical and intuitive sense, which, well, really works out very, very, very well for us because that means not only do we get to sit there and use fancy words to explain what's happening, we can also show it with math. So to recap thus far, the Solow model has a number of really nice properties. We've seen a unique steady state, right? We've seen global asymptotic stability, and we've seen some pretty simple and intuitive comparative statics, but we've really seen like zero growth. And it's called the Solow growth model. So what the hell, right? We've got a growth model with no growth. How the hell does that work? Well, remember, the steady state is the point at which there's no growth in the capital labor ratio. There's no more capital investment, no more increases in output. And thus, without any technological progress, nothing gets the Solow model to grow. The model only generates growth along that transition path towards the steady state. Growth isn't sustained. It eventually slows down and goes to zero when we reach the steady state, right? So if we're here, as we're getting more capital and we're converging towards steady state capital, well, output is increasing, but it's increasing along the output curve. We're not getting any real growth, right? We want growth here, right? Just increasing output by increasing capital isn't really growth because we're still on the same growth curve. What if we want to be on a different growth curve? Well, let's talk about how. So we solved out the steady states. We can see how everything is in a dynamic equilibrium. We get markets clearing. They trend towards their steady states where nothing changes. It's a steady state, right? So these steady states aren't super interesting in the sense that, we're assuming economies are in the steady state. Instead, they're interesting because it gives us a state of rest that we can then disturb through stochastic shocks. So we put everything at rest, right? Things aren't really moving because they're at rest. So we minimize the number of moving parts. And if we can do so, right, we can then select things that we're actually interested in and isolate the effects of only that change. So these movements aren't being contaminated by other movements. It's kind of like having controls in a scientific experiment, right? You want everything to remain constant except that one little thing you want to tweak. So if we can do that, right, we put everything into a steady state, and then we can change something. We can see how things will change based on just that one guy moving, not everything else as well. So how would Solow grow? Well, remember the steady states are given by this right here. We've got steady state capital, steady state output, YSS, steady state investment, ISS, and then the difference between steady state output and steady state investment is steady state consumption. Okay. Cool. We got that. That's good to know. But it doesn't get at the question that we asked in the title, does it? How does Solow grow? Because you see, in the steady state, there is no source of growth. And when we achieve steady state capital, we achieve steady state output, consumption, and investment. The economy is at rest. All the endogenous variables are at rest. So there's no source of growth in the economy. So in the context of growth, we're not really interested in moving to a new point on the same output curve that we have right here on slide 20. All right? If, say, I've got steady state capital here, right? But then, I want to produce more. What would I have to do? I'd have to save more capital. Okay, well, then I just get up here. But, okay, that's on the same curve, right? There's no technology changing. It's just increasing capital. I mean, capital's good. I'm not saying it's, a bad thing, but just adding capital isn't going to drive economic growth. So what does? Well, if investing just gives a slightly higher output, that's nice, but what's happening is that marginal product of labor and capital, the fact that it's falling is kind of screwing with us here because we're not really getting enough of an increase in output to actually trigger economic growth. Because the more capital I add, the more output I get, but every additional unit of capital becomes a little bit less productive than the one that was before it. All right, it's always going to be productive, but the amount by which it adds, like productivity, diminishes. So the marginal product of labor and the marginal product of capital will fall, and the fact that it falls messes with us because we're not really getting any growth. We need to find a way to make that capital and that labor more productive. Because if that's the case, then we can get more with the same number of resources. If we get more with the same amount of capital and labor that we were using previously, but we use it more efficiently, then that's actually growth. So to trigger growth, we want to shift output up. We want to make the output curve shift, which means essentially we're using the existing resources just in a much more efficient way. And it lets us produce more, and it lets us be better at producing more than before. Right? None of the endogenous variables will be shifting the output curve, or really any of the others. So instead, we need to see what will shift output. And I'm going to give you a hint here. It's AT. If I shift total factor productivity, then I shift output up. And so I really need to now think about what would be causing an increase in total factor productivity and where it comes from. So I'm going to ask, where does it come from? Well, the shock to total factor productivity is the result of somebody getting a cool, super awesome new idea. And this idea lets us do something in a better way, which makes production more efficient. So suppose somebody develops a warp drive engine, right? So spaceships can travel faster than the speed of light. You think that's going to make production easier? Probably. I can think of a few ways that it would. If you can't, I highly suggest you watch a couple episodes of Star Trek. You'll get a pretty awesome idea as to how it will be. Star Trek is fantastic. Everything before 2009. And then the third season of Picard. That third season of Picard is actually fantastic. But everything between 2009 and the third season of Star Trek Picard is garbage. Don't watch it. Okay, so let's come back down to Earth and reality. Let's talk about Henry Ford, right? We all know who Henry Ford was. He started the Ford Motor Company. Oh, cool. He made cars. His biggest contribution, though, is really the automation of car manufacturing, right? Kind of setting up the assembly line. If we have an assembly line, it makes for a very, very, very efficient production process. All right, so let's say we're alive back then, right? And we see this assembly line. So we see this car kind of being built in stages with different people working on different parts of the car. They specialize in certain parts very, very, very well. And that's the one thing that they really, really, really know, so they can contribute that one little bit to the car, and then they pass it off to somebody else who does their part on it. And then the car gets built essentially at the hands of experts in these individual little subject matters. So, Okay, let's say we are alive back then. We can't really steal the plans for his car and the process and then copy the car. That's copyright infringement. We'd get sued, and it's just wrong, right? Don't steal somebody else's idea. Come up with your own. We can do is take that process and put it towards something else. So I can't say, hey, I just want to make the exact same car the exact same way. But I can go, I want to make a different product in a similar way. So I can take that process of production, I can take that assembly line process, and I can put it towards something else. Say I want to make radios. Well, I can now use an assembly line production process that Ford came up with, but I can do it for a radio instead of, say, a car. So what I did, or we did, not just me, we took the idea that Ford came up with and we ran with it, right? We did our own thing. That idea is an example of total factor productivity. It's driven through an increase in A sub t. When we get total factor productivity, right, we're getting an increase in AT, the output curve shifts up because we can produce more with the same amount of resources, right? Because if we're in the car manufacturing process, we didn't get any more resources than before. We had the same number of people and the same amount of capital. It's just we had each person contributing their own little bit in stages. So we're producing much more efficiently. So we can make more cars in the same amount of time. Because not only are these people like experts in that one particular production process of the car, they don't have to change gears. No pun intended. They can focus on just that one thing, right? So if you're, say, putting the wheels on the car, okay, that's the only thing you do. Yeah, it's probably monotonous and tedious as hell. But you're not going, well, I just put the wheels on. Now I need to, I don't know, put the bumper on or drop the engine in, right? To do that, it's going to take time to switch from one task to the other, not just physically, but also mentally. It's a lot better to just focus on one thing. So if you're focusing on that one thing, you get really, really, really good at it and you can do it really quickly. Thus, we can make more cars in the same amount of time. So we're using the same amount of resources, right? We're using the same amount of time. We're using the same number of people and the same number of things to produce, but we're just using them more efficiently. And there are so many other inventions that have made production easier, right? There's the cellular phone, there's the computer, there's the cotton gin, the printing press. Really, those last three, are big drivers for either the cause of certain wars or the end of certain wars, right? The printing press, okay, well, it kind of helped spread a lot of ideas that fueled the American Revolution. The cotton gin, we all know that one's contribution to the start of the Civil War and the end of slavery. The computer, well, really helped end World War II. Think about the B-29 bomber with the gunners being entirely inside the fuselage of the bomber. They didn't have to be outside of the bomber. They didn't have to have any open windows. They could stay entirely inside a nice pressurized cabin and just kind of look out a window, and there was like an old school super analog computer that would essentially help line up their sight with the line of sight of the gun and help shoot down enemy planes. Pretty cool stuff. I know, I'm a big World War II fan. But all of these things here are incredibly awesome achievements, technologically speaking, and they've made production and really just life in general much easier overall. So maybe think about a couple other inventions that have really had major impacts on the world. Now, I know I kind of took some of the easy ones, right? I took, the phone, the computer, the printing press. I took the internal combustion engine earlier. So really try to think about some other things that have really been a major contributing factor to society being the way that it is now. And, it's really not going to be hard. Just try to think about it on your own and think about how, that could have made production easier. Not just that it did, but also think about how. Okay, so how does Solow grow? Well, let's say we start with an increase in AT, right? Because that's going to be shifting our output curve. So I've got the original output curve, Y0 equals A0 times KT to the alpha. That's what we see in black here, right? So the black curve is Y0 equals A0 times K to the alpha. And at that point, we've got our steady state capital and our steady state output. Now, I didn't graph out investment here or depreciation. I didn't want to overcrowd the image, but if you had this, you could easily draw out investment, depreciation, and figure out what the steady state capitals would be, and kind of how the investment curve and depreciation would line up accordingly. So I'm starting at Y naught, right? YSS naught here, right here. I'm starting here with this amount of capital with output defined right here. Now, let's say I increase A, right? And the only thing that's going to change here is A. When I do that, no other variables change. Capital doesn't change. Labor doesn't change. What happens is I'm going to shift from the black curve up to the blue curve. I'm going to shift from here up to here. Note, steady state capital is the same, but steady state output increased. So the only input that changed was A. A naught increases up to A1. So the vertical distance of that shift is the shift that's driven entirely from A. So if someone in an economy gets like a cool new idea that helps the economy out, the economy can use the same number of resources to produce more. And that's what actually allows economies to grow. Every new idea someone gets helps the economy grow more and more. Right? Maybe not every new idea. Some new ideas are complete crap, but every new idea that is considered useful, that can aid in the production process, makes workers more efficient. It makes capital more efficient. It's a better use of your time. You can do more. Thus, we are shifting output upwards. Now, another thing that's awesome about this is that when we get ideas, right, these ideas don't depreciate like capital does. Capital falls apart over time. It's a physical object. It's not going to last forever. Ideas, on the other hand, aren't going to fall apart, right? It's not like, oh, well, you know, I came up with the idea for the internal combustion engine, and then that idea just falls apart, and for some reason we forget how to make the internal combustion engine. No, right? We know how to make it. We know what it does. Maybe you couldn't build one yourself, but you probably have a pretty good idea of how it works. So once that idea is put into place, it's not going to fall apart. But what you can do is you can take that idea and you can build on it, or you can add something else to it. You can go, hey, this is a cool thing. Let's take that and then try to do our own little twist on it. So we keep building on existing ideas, right? So once you invent something, I know it says invest, but it's really supposed to be invent. Once you invent something, no one else has to reinvent it, right? It's there to be used forever. And once, really / if, this can be used without any sort of intellectual property right violation, meaning it really becomes public domain, that technology is then readily available to be used by everyone, and it makes the world a better place because you all get to go, hey, that's a cool idea. How do I make it better? Let's go through another example. You ever see that movie, The Founder? If you haven't, I highly suggest it. It's a really cool movie. It's kind of going back to that assembly line process, except instead of making cars or radios, it's making McDonald's cheeseburgers. Right? The McDonald brothers figured out exactly how to set up the most efficient procedure that they could possibly make to produce a cheeseburger. And in the movie, what they do is they set everything up on a tennis court, and they try to see what the quickest way was to get the raw ingredients put together. And it was passed along like an assembly line, quote unquote, to be produced into a finished burger. And that process, right, once it was adopted by other firms, made everything work much better than before, and the economy became more efficient, right? So McDonald's comes up with it, and then let's say, I don't know, like Burger King or Wendy's, we're like, hey, it's a pretty cool idea. Why don't we do something like that? And then they adopt it. Well, they adopt it. Okay, it kind of sucks for McDonald's, but it's also a lot better for the consumer because now there's more competition. The price of the burger is going to fall, and the consumer gets more choices. It's pretty good stuff, right? I like to think so. So, with all that out of the way, this is where I admit to having lied. I wasn't lying at the time. So there's at least that. I just didn't realize that I wasn't being truthful at the moment. Whatever. This isn't going to be a 2-part lecture. It's really going to be a 3-part lecture. Now, the next part, we're really just going to purely talk intuition. I don't think there's going to be even a single equation on the page anywhere. It's really just going to sort of tie up some of the ideas of the Solow growth model. And then that finishes chapter 7. And, well, we move on to chapter 8 from there, where we can talk about some theoretical observations of the Solow model. Really, like, how does the Solow model hold up against the real world data? What works, what doesn't? For things that don't work, what can we do to improve those things, right? Because remember, going back to ideas appreciating, Bob Solow got the idea for this model. Pretty cool stuff. But, it wasn't perfect. So what can we do to improve it? Well, there are certain things. And we'll talk about that in chapter 8. And then that wraps up really the first overall section of the course, where we will then spend the remainder of the course doing business cycle macro stuff. And that's where things get like really, really, really cool. We learn about like recessions, monetary policy, all that. But that is for a later date after the first exam. So just a heads up, the first exam will be coming relatively soon, although I will be announcing it pretty far in advance, and you'll have a study guide to play around with, so you won't be completely in the dark on what kinds of questions I'll be asking. So I guess with all that out of the way, I'm just going to wrap up the video. Thanks for watching, and I will see you next week.